All right, today what we're going to do is we're going to figure out some rules that are going to allow us to take derivatives of polynomial functions and also, well, some stuff that kind of looks like a polynomial even though it's not technically a polynomial. We'll mention those rules, although the proofs for those rules will come a bit later. So remember that what we've been talking about here are derivatives. And the reason we're interested in derivatives is because they express the rate at which functions are changing. Of course, this rate at which a function is changing is a rather important concept for many applications. Like Newton was interested in this stuff because he was interested in physics. And so if you're talking about positions, well, the rate at which position is changing is velocity. The rate at which velocity is changing is acceleration. And if you know a little bit of physics, maybe from high school or wherever, you'll know that, of course, Newton's laws involve acceleration and things. So there's all kinds of things going on here where this is interesting. And it has many other applications as well. We'll see some of those later. But just for the moment, you can kind of think about how, a lot of the time we really care about how something is changing. And we figured out, mathematically, you can calculate the rate at which a quantity is changing by saying it is the derivative f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x divided by h. Now, really what this is it's just the difference quotient, in other words, the average rate of change in the limit as our interval over which we're taking the average is shrinking down to 0. So that's all we're doing here. And the thing that we've spent all this time doing is making sure we precisely understand what it means to take this limit. What do we mean by saying we want to shrink this thing to 0? And last week, of course, we looked at examples of calculating this stuff. But the way that we were calculating things is we actually just wrote down this difference quotient, or the limit of this difference quotient, I should say, in specific cases for specific functions f, and then we use the rules that we figured out for limits to calculate what that derivative would be. Now that works fine if you have a reasonably simple function. It's not too difficult to do this if this is just a nice function like, 3 times x, or x squared even is not so bad. But the problem is that this would become rather annoyingly long and difficult to do if we had a more complicated expression to work with. So if I had some big, long polynomial, and I tried to use this definition directly, I would end up with this enormous mess. I mean, you can play around with it for a minute. I'm not going to try to write down any particularly messy examples, but play around, like write down a degree 6 polynomial with 6 terms, and look at what the limit looks like. It turns into a huge kind of mess. We can do it. We certainly can do it, but we would like to see if we could find some shortcuts. And the answer is yes. There are shortcuts for calculating what this limit comes out to be without having to explicitly refer back to the limit itself. And that's what I want to look at today. So we're going to look at some basic rules for derivatives. And then we'll see how these basic rules are going to apply to calculating the derivatives of stuff like polynomials. So, to begin with, the derivative of a constant, and remember, I can write derivative with this d over dx notation, the derivative of any constant is equal to 0. This is really pretty simple to show because I'm taking the limit as h goes to 0 of k minus k divided by h. This is the limit as h goes to 0 of 0 over h. Well, of course, that is just equal to 0, so we're done. In fact, we've seen this before. I think I wrote this down last week, kind of as an observation in passing. But I want to repeat it here because it's important, even though it's fairly straightforward to show. Now, the next thing that we can show is the derivative of a function that is just equal to x. This is also called the identity function because if f of x equals x, then whatever you plug in, that's what comes out. It leaves the identity unchanged, so it's called the identity function. The derivative of this is equal to 1. And again, this isn't too terribly difficult to show. We've kind of done harder stuff before, honestly, because this is the limit as h goes to 0 of x plus h minus x divided by h. Well, the x's here are going to end up canceling out, and we get the limit as h goes to 0 of h over h. The h's cancel out and leave me with 1, and so, of course, this is just equal to 1. And, of course, this is not a surprise, right? If you think about what does the graph y equals x look like, it is a straight line and it has a slope of 1. Well, that means that the tangent at every single point should be a slope of 1, and that's exactly what we see here. Like, this is not some kind of shocking new information here. Okay, so now we're going to move on to a slightly more complicated question. And we're going to see if we can do this one. Well, again, we've kind of done this before. So let's do one warm-up case, and then we'll move on to the more general case. Our goal here is to deal with x to the n, where n is a natural number. But I'm going to start by doing x squared. So what if I just want to take the derivative of x squared? Well, this would be the limit as h goes to 0 of x plus h squared minus x squared divided by h. Okay, that's nice. I can expand this out by using the rules for squaring binomials, and I get that this is x squared plus 2xh plus h squared. Then, of course, I still have a minus x squared, and then I have divided by h. So it's a little bit lengthy because, of course, we're expanding out the x plus h, but not too terrible or anything. X squared minus x squared, that cancels. And I'm noticing here that everything else has an h in it. So let me write down what I get here. I can factor an h out, and this becomes h times 2x plus h, all divided by h. Well, the numerator h and the denominator h now cancel because both the numerator and the denominator have a factor of h. Okay, but now this is a polynomial in h, and therefore, as h goes to 0, I can take this limit by just plugging in h equals 0, and I am left with 2x. So the derivative of x squared is just 2x. Now, we can actually use this same idea to take the derivative of x to the nth power. And how do we do this? Well, here's the thing that I want to remind you of for this process. We need something called the binomial theorem. Actually, we only need part of the binomial theorem, so I'm going to tell you the part that we need. What the binomial theorem says, I'm sorry, I'm tripping over my Coke here on the floor, so excuse me for a second. What the binomial theorem says in general is rather complicated, but we only need this part of it. If I take a plus b and I raise it to the nth power, where n here is a natural number, so a counting number like 1, 2, 3, 4, so on, a positive integer, then I get a to the n plus b, a to the n minus 1, plus b squared times a bunch of stuff. And the point is, all of this stuff has at least a b squared in it. In other words, I can factor a b squared out of all of this stuff. The full binomial theorem actually tells me exactly what this stuff is. I'm sorry, I screwed this up, didn't I? This is supposed to be n, b times a to the n minus 1. Everything else has a b squared in it, and this has an n, which I managed to not write the first time that I wrote this down. Sorry about that. The full binomial theorem would tell me what all this stuff is, but I don't actually care. And there's a reason I don't care, which we will see in a moment. So keep this binomial theorem in mind as we work the next question. Let's figure out the derivative of x to the n. This is going to be the limit as h goes to 0 of x plus h to the n minus x to the n, all divided by h. Now you can see here why I wrote down the binomial theorem, right? I have a binomial here raised to the nth power. That is exactly what I need this binomial theorem for. Now, in fact, I'm going to encourage you, take a moment for yourselves, pause this, and see if you can work out what this limit comes out to be using the binomial theorem here before you watch through this. I don't expect everybody will necessarily be able to figure this out, but I think it's good to spend a minute thinking about it in any case. And if you do get it, then good for you. That's really excellent if you can figure that out for yourselves. All right, so hopefully you guys were able to figure it out or at least see some interesting stuff here. Let's go through this and see exactly how we do calculate this limit. Now, what I want to do here is to use this binomial theorem. And in this case, I have a equals x and b equals h. Sorry, that's really small, but I don't have a lot of space to write that part. A is like x, b is my h here. So this is going to become the limit of x to the n plus n times h times x to the n minus 1 plus h squared times a bunch of stuff that's going to be a polynomial in a and b, because I should mention that all of this stuff is some polynomial in a and b in the binomial theorem. So this is a polynomial in h and x. And then I'm subtracting x to the n. All of that is now going to be divided by h. Now, my x to the n's cancel. Everything else up here is going to have an h in it. So I can rewrite this as the limit as h goes to 0 of h times n x to the n minus 1 plus h times some polynomial in x and h. All of this is divided by h. My h's will now cancel with each other on the top and the bottom. These two that I just crossed out. I have another h in here, but that doesn't cancel with anything, which is actually good because now that I've canceled the h in the denominator, I can take this limit by just plugging in h equals 0. Well, that means I have 0 times a polynomial in x and h. 0 times any polynomial just gives me 0. And therefore, what I am left with is n times x to the n minus 1. So what we have figured out here is that to take the derivative of x to the nth power, you multiply by the power, and you decrease the power by 1. This is also sometimes called the power rule for differentiation. So, what we've proved this for is we've proved it for the natural numbers. Now, it turns out later on we will see that this power rule, that the derivative of x to the n is n times x to the n minus 1, this is actually true for all n not equal to 0. So we've only established it for the positive integers here, the natural numbers. However, as we will see in a little bit, it's also possible to prove that actually this rule is true for arbitrary powers as long as that power is not equal to 0. In the case of 0, you could kind of say, well, it's almost true because you're multiplying by 0. But then you also are dividing by 0, and it's best to just exclude that as a special case that we're not going to deal with by this rule. If it's x to the 0, then we're really just dealing with the derivative of a constant anyway, so we know how to handle that. The derivative of a constant is just 0. Okay, so we're going to allow ourselves to use this rule for any n not equal to 0, any real number not equal to 0. But as I say, we've only established it so far for the positive integers. The reason for that is because after we prove a few more rules, we'll come back and we'll see why this is true in general. And it turns out that it's not too difficult to see once we have those extra rules. So I will save us some time on going through really technical and annoying calculations, and we'll just use those rules later to justify what we said here. We'll prove the rules that we need later, which are the product rule and the chain rule, without referencing this rule at all. And so there's no circular logic going on here. That is one thing you got to be careful about in mathematics. When you are approaching a new topic, you want to make sure that you don't use any circular reasoning. You can't assume the thing that you're trying to prove. So if I wanted this to be true for all n, but to prove it, I had to assume that it's true for all n, well, that would be bad. However, we're not going to be doing that. We're not getting to those rules yet. So I will leave this as, yeah, this is just the rule in general. Now, two more rules that we need to do in order to handle polynomials. So the first rule is this. If the derivative of f of x equals f prime of x exists, then the derivative of a constant times f of x, this is going to be the limit as h goes to 0 of k times f of x plus h minus k times f of x, all divided by h. But I can factor a k out of this and bring it outside the limit. And here I will write down what we get. But here, what we have is just k times the derivative of f, which we said exists. I can bring the k outside the limit because that is one of our limit laws. If there's a constant multiplying the entire thing inside the limit, then I can bring it outside of the limit, as long as that limit exists, which in this case it does, because this limit is literally just f prime of x. So, the derivative of a constant times f of x is the constant times f prime of x. It's a very interesting result. So it tells us we can bring constant factors outside of our derivatives. There's a second rule for differentiation that is really important and which will finish off everything we need to differentiate polynomials, and that is the following. The derivative of f of x plus g of x, if f prime of x and g prime of x exist, what is this going to come out to be? Well, this is going to be the limit as h goes to 0 of f of x plus h plus g of x plus h minus f of x plus g of x, all divided by h. But here's what I can do. I can rewrite this as the limit as h goes to 0, f of x plus h minus f of x plus g of x plus h minus g of x, all divided by h. And this is going to be the limit as h goes to 0, f of x plus h minus f of x, divided by h, plus I can split the limit here. The limit as h goes to 0, g of x plus h minus g of x, all divided by h. So I can take this fraction and split it into two fractions that are added together, and then I split those two fractions added together into two separate limits. I am allowed to do this as long as these limits exist. But can you see why these limits exist? Take a minute to think about why each of these limits separately exists, and think about what we assumed in this problem. So hopefully what you notice is that actually this limit here is just f prime of x, and this limit here is just g prime of x. Okay, that doesn't look much like a g. There we go. G prime of x. And that is why they exist. We assumed from the beginning that these exist. And therefore, what we can say is that if the derivatives exist separately, what we have established here, let's write it down up top. I'm going to have to erase this, but this way we have the rule written down compactly. What we get is that this is equal to f prime of x plus g prime of x. In other words, the derivative of the sum is the sum of the derivatives. Now, I do want to make a quick caveat here because you got to be careful. This only works in one direction. So if the derivatives exist, then you can use this rule. But you can't say, just because the derivatives don't exist, that this derivative doesn't exist, okay? That is not necessarily true. There are examples of functions which cannot be differentiated, but their sums can be differentiated. For example, any function plus -1 times that function is just 0, and 0 can always be differentiated. So we cannot go in the other direction. We can't say, if these don't exist, this derivative doesn't exist. We have to be more clever about trying to figure out whether this derivative exists if we're going to be able to establish it. So the nice thing is that if these derivatives exist separately, then we can just apply this rule and we're done. But if these derivatives don't exist, then we're going to have to be a little more clever about what we're doing. And if for some reason we still need to deal with that. Now, here's the good news. Mostly in this class, we'll be dealing with sums where each of the thing in the sum is going to be differentiable by itself, so we can usually use this rule. And this is also known as the sum rule for derivatives. Remember that we had a sum rule for limits as well. Don't confuse the two. So there's the sum rule for limits, then there's this sum rule for derivatives. All right, so there is one more variation on this sum rule that we can mention here. The derivative of if f prime and g prime both exist, if I have f of x, actually, let me just write it this way. The derivative of a times f of x plus b times g of x, using the rules that we have here, assuming that these derivatives exist, this is just going to be equal to a times f prime of x plus b times g prime of x. Why? Well, I apply the sum rule to split this into the derivatives of each of these terms, and then I use the constant multiple rule that we figured out back how long ago was it? It was like 5 minutes ago. I don't remember exactly when it was, but go back a bit. We had this rule that says the derivative of a constant times a function is the constant times the derivative. Now, this means that d by dx, the process of differentiation, is what is called in mathematics a linear operator. What is a linear operator? An operator is something which takes a function and gives you back a function. Actually, an operator is more general than that, but one type of operator is something which it's kind of like a function, except it takes as its input a function and it gives you back a function. So instead of taking in a number and giving you another number, it takes in a function and it gives you back another function. Linear refers to this property, the fact that you can factor out constants and you can split it over sums. It turns out that linear operators are some of the most important things in mathematics, and the derivative is an example of a linear operator. So I just wanted you to know this in case you happen to see this in future, you'll know what it is that you are talking about. Now, let's see how we can use the fact that the derivative is a linear operator together with our power rule to differentiate polynomials. So let's suppose that I wanted to compute the derivative of 2x to the fourth minus 3x cubed. Now, I could certainly go back to the definition of the derivative and try to work this thing out sort of by hand, so to speak. But I'm not going to do that. I want to try to apply these rules. Well, what I'm going to do is I'm going to say, okay, each of these things is just a constant times a power of x. So each of these things is differentiable separately. And therefore, I can say this is the derivative of 2x to the fourth plus the derivative of negative 3x cubed. Therefore, I can then say, well, I can bring out these constants. So this becomes 2 times the derivative of x to the fourth minus 3 times the derivative of x cubed. Now, can you figure out what is the derivative of x to the fourth and what is the derivative of x cubed? Let me give you a minute to think back to your power rule and see what that becomes. So for x to the fourth, I have to multiply by 4 and decrease the exponent by 1. For x cubed, I have to multiply by 3 and decrease the exponent by 1. So what I end up with when I do all of these operations that I've got written down, 2 times 4 is 8, of course, and then 4 minus 1 is 3, and then negative 3 times 3 is negative 9, 3 minus 1 is 2. So we end up with 8x cubed minus 9x squared. Now I want to notice here, you can actually get to the point where you can just read this off immediately, because when you do the sum rule, the constant multiple rule, and the power rule for these polynomials, what are you really going to end up doing? Well, each term gets multiplied by its exponent, and the exponent gets decreased by 1. That's literally all you're doing. So I could have from the start said, okay, 4 times 2 is 8. 4 minus 1 is 3. That's going to give me 8x cubed. Negative 3 times 3 is negative 9. 3 minus 1 is 2. That gives me negative 9x squared. And I could have written this down all in one shot. So let's take a look at another example where I'm going to try to do all of these steps sort of combined into one so that you can see how that works. And then if it's not clear to you how that happens, write it out step by step to make sure that you follow it. But let's suppose now that I want to do the derivative of 1/2 x to the fourth minus 3x squared plus 2x. And then let's do plus 3. So what I'm going to do here is I'm just going to say, okay, on the first term, I multiply by 4. So what is 4 times 1/2? Well, that just comes out to be 2. And I decrease the exponent by 1, so that becomes x cubed. Then I take the next term. 2 times negative 3 would give me negative 6. 2 minus 1 gives me 1, so this just is left with an x raised to the 1. Now, the next one is 2 times the derivative of x. That's just 2 times 1. I'm just going to leave that as a 2. So remembering that the derivative of x is 1, we have 2 times 1, and we're done. And what is the derivative of a constant? Do you remember? We figured that out right at the beginning. The derivative of a constant is 0, so that just goes away entirely. All right, so let's write down some examples here. And I'm going to ask you to take just a minute and think about them yourselves, and then we'll go through them together and see what we get. So suppose that you want to do the derivatives of, let's say, 7x to the fifth plus 4x cubed minus 1/2 x squared. And then we'll also do the derivative of negative 9x to the eighth plus 7x to the fifth minus 3x squared plus 2. All right, so pause the video, take a couple of minutes, see if you can work these out, and then come back to this and we'll keep going. So were you able to do it? Let's take a look at how we would do this first one. I look at the first term. The exponent is 5, so I have to multiply by 5. Now, what is 5 times 7? Well, that's 35. Then 5 minus 1 becomes 4. What about the next term? Well, 3 times 4 is 12, and the cubed exponent becomes a squared exponent. For the last term, 2 times negative 1/2 becomes negative 1, and 2 minus 1 becomes 1, so we just get minus x. And there we go, there is our derivative. What about this second example? Well, 8 times negative 9, that gives me negative 72. And then I get x to the 7. Actually, I now have another 7x to the 5th, which is going to become another 35x to the 4th. I say another, but I mean like another just like in the first example. It's separate example, separate problem here. Then negative 3 times 2, that becomes negative 6, and I have an x. And then the derivative of the constant is 0, so we just throw that part away. So there's our derivatives here. And of course, we can use these derivatives any way that we want to. So all of the applications of derivatives that we looked at last week, we can still use that stuff here. And we can say, okay, let's suppose that I want to find the tangent line to y equals 1/3 x to the 6th minus 4x squared at x equals 2. So the first thing that we want to do is we want to figure out what is the point that this thing is going to go through. So the point is going to be 2 comma 1/3 times 2 to the 6th minus 4 times 2 squared. So this is going to be, let's see, the x value is still 2. Now, 2 to the 6th, that is 64. So this is going to be 64 over 3 minus 16. And what is 16? Well, that is 48 over 3. So 64 minus 48 is 16. So this becomes 2 comma 16 over 3. So that is the point where this function is going through at x equals 2. And so that is important because our tangent line has to go through that point. Now, to find the slope, we need to look at the derivative here. There's a couple of ways of writing the derivative, by the way, when one variable is set equal to another. We can write y prime, so we kind of use the same prime notation as for functions for this variable, or we can write dy over dx. So we just kind of treat the dependent variable in our notation as if it's a function of the other variable, because that's kind of what it is. When one variable is a dependent variable on the other variable, really what we're getting is this kind of, it's really just kind of a function of the other variable. So regardless of which notation we choose to use, this is going to become 6 times 1/3, this is 2, excuse me, I'm choking myself here, 2 times x to the 5th. Because, 6 times 1/3 is 2, 6 minus 1 is 5. Then we're going to have minus 8x, just x. So we have 2x to the 5th minus 8x. So if I evaluate at 2, I'm going to have 2 times 2 to the 5th minus 8 times 2. Well, this is going to be 64 minus 16, which is 48. So this is going to be my slope for my tangent line. And now I use the point and I use the slope. So we get y minus 16 over 3 is equal to 48 times x minus 2. And there is my tangent line. Okay, I just drew the box straight through the equation. That was really great of me. There we go. Now you can hopefully read the entire equation. So these shortcuts really, really help us out a lot when we do this stuff, okay? What they are doing for us is they're allowing us to just kind of look at the polynomial and write down the derivative according to a few simple rules. And then we can use that derivative for, well, any of the stuff you can use derivatives for. It's just the derivative, but we've managed to do it without ever having to write down a limit. Now, I want to emphasize, it's not that we're calculating these without using limits. We are using the limits. But just as when we calculate limits using limit laws, we're not having to directly refer back to the definition and the epsilon delta stuff. The point is, we use the definition of a limit to prove that there are certain rules that will always work. So our rules depend upon those definitions. And that's why we needed to do those definitions first. We can't just say, let's define the derivative to mean we use these rules, because that wouldn't show us that these rules actually work for anything. So even though I didn't explicitly refer to a limit here, everything I did in this problem depends upon the limits and depends upon that limit definition, because all of the rules I just used depend upon that limit definition of the derivative. All right, I'm going to end this particular video here for the moment. What we are going to do next is we are going to take a look at the derivatives of exponential functions. And the derivatives of exponential functions actually turn out to be very nice, although a little bit annoying to definitively prove that they exist. But it turns out that they're not that difficult to calculate. And that will give us this really, really, really nice way of taking those derivatives. So that will be our next task. And then we'll look at what happens when you multiply or divide functions.